Good day and welcome back. Today we're going to study a few graphs of induced EMF in three cases. First is about the wire that moving across a magnetic field. So I will use one example from the trial of SMK Yu Hua in 2020. You are given with a magnetic field regions of PQRS where the length of RS is given as 3 cm. And you have a wire loop of ABCD with the length of A and the width of B. The wire will move across the magnetic field with a constant velocity. So you are given with a graph of induced EMF against the time. For the graph, we can separate into 4 sections for the next discussion. First is from the 0 to the first second. So we can see that there is no induced EMF when the wire is moving from the left up to the line PR. Up to this point, there is no magnetic flux linkage, so there will be no induced EMF in the wire. Then the second part, the wire is going to enter into the magnetic field regions. From the graph, we can see that there's an induced EMF of negative 40 millivolt in the wire. Based on what we have learned before, that we use Faraday's law to derive the induced EMF in the conductor. As we can see that there's increase in the magnetic flux linkage in the conductor, so there's induced EMF trying to reduce the magnetic flux linkage. From the derivations, we can obtain the induced EMF is equal to negative flux density multiply the width of the conductor B multiply the velocity of the conductor. Next, we look at the third section where the wire continues to move until the line QS. As you can see, there is no change in area that link to the magnetic field. So the rate of change of the area is equal to 0. So from here, there is no change in magnetic flux linkage. So there is no induced EMF in the conductor. And then we move on to the fourth section. As you can see, the wire is start to exit the magnetic field region. There will be decrease in the magnetic flux linkage. This would cause an EMF is induced in the conductor to increase the magnetic flux linkage. If we repeat the derivations, so you will get the same equations as what we did in the second section, except that the induced EMF now is positive value since the rate of change of magnetic flux is a negative value, which means the magnetic flux linkage is decreasing. Now let us try to answer the questions in the trial paper. First is to calculate the velocity of the conductor. From what we have discussed, that the wire BD is moving from PR to QS at the time of first second to the fourth second. With this, we can calculate the velocity by using the formula of distance divided by time, where the distance is the 3 cm and the time would be 4 minus 1 millisecond. In the end, we will obtain the velocity as 10 meters per second. Next is to find the length of A and B. So once again, we can apply the formula of the velocity, that the time taken for the wire to fully enter the magnetic field regions is between first and the third second. So the velocity is equal to the ratio of the A and the time. So we can obtain the length of A by the product of B and T, put in the values, and you will get the answer of 0.02 meter. Next is the length of B. So you can apply the formula of the induced EMF that it is equal to negative BBV. Put in all the value that the flux density is given as 0.3 Tesla. In the end, you will get B is equal to 0.013 meter. Next, we move on to the rotating coil. So I would use one example from the trial of King George in 2020. So you are given with this diagram. So you could see that the coil is connected to a slip rings that produce an AC current. You are given with the number of turns, area of the coil, frequency of the rotations, and also the flux density. From the frequency of 50 rotations per second, we can calculate the angular frequency, which is equal to 2 pi f, and it is equal to 100 pi per second. With this, we're going to derive the formula of the phi, which is equal to NBA cos omega t. Put in all the value, and you can get that the phi is equal to 1125 cos 100 pi t. With the equations, we can plot the graph response of the magnetic flux that it is a cosine graph with the amplitude of 1125 Weber. Next, we're going to derive the induced EMF by using the Faraday's law. It is equal to negative derivative of the magnetic flux. Substitute the expression of the magnetic flux, and you would get induced EMF equal to 112,500 pi multiplied sine 100 pi t. So I went through the graph of the EMF with you, that the amplitude of this graph in this case would be 112,500 pi. Now you can observe the first graph, that the gradient of each point in this graph is representing the negative of induced EMF. So from the graph, we also can link to what we have discussed previously about the magnetic flux linkage and also the induced EMF. We have learned that the induced EMF also can be obtained by the cross product of the velocity and the flux density. When the coil is perpendicular to the magnetic field, we can see that magnetic flux linked to the coil is at maximum value, which would be 1125 Weber in this case. However, the motion of the coil is in parallel to the magnetic field. So if we apply the cross product of the velocity and the flux density, it will be a zero value, which would be the minimum in this case. Next, we're going to look at the second case where the coil is in parallel to the directions of the magnetic field. So the magnetic flux linkage will be zero in this case, since the normal component of the magnetic field linked to the coil is zero. But we can see that the motion of the coil is in perpendicular to direction of the magnetic field. If we apply the cross product of the velocity and the flux density, this would give us the maximum value that the induced EMF is also maximum at this point. Next, we're going to talk about the example of the self-inductance in SMK Yu Hua 2020. You are given with a circuit of battery 12 volts connected to 5 Henry inductor and 6 volt resistor. To avoid confusions, I will label the voltage across the inductor and resistor as VL and VR respectively. From the topic of self-inductance, we learned that the induced EMF or the back EMF is given as negative L multiplied di dt. From the circuit, when we close the switch initially, the current will increase from 0 ampere to a certain steady state value. So the initial voltage across the resistor will be equal to 0 since the initial current is equal to 0 ampere. So the induced EMF will be equal to negative of EMF value. Put in the formula that you will get negative 12 equal to negative 5 multiply the initial rate of change of current. Solving the questions will give you the initial value of the rate of change of current equal to 2.4 ampere per second. So from what we have learned that the current will slowly increase up to a steady state value. At that time, induced EMF will be equal to 0, that there will be no voltage across the inductor. So now we can treat the inductor as short circuit at this time. This means that we can ignore the inductor at the steady state value, and we can use the formula of V equal to IR. So the current flow through the resistor will be equal to 12 divided by 6 equal to 2 ampere. So we have learned about the graph response of the current flowing in the circuit, where the steady state value will be equal to 2 ampere. And then we also have learned how to sketch the graph of the induced EMF. From the discussion, we have learned that the initial back EMF of the inductor will be equal to negative 12 volts. And then the back EMF will be slowly turned into 0 when the switch is open. So there will be a back EMF induced in the inductor to oppose the change in the current. To find the value of the back EMF, if you are given with the rate of change of the current, you can substitute in the formula to obtain the back EMF. But if you are only given with the time of the current falling to 0, we will not get the actual peak value of the back EMF, but only the average induced EMF. Substitute in the value, and you will get 50 watts as the average induced EMF in this case. So that's all for my discussion of these three types of graph. If you have any questions, you can leave it in the comment section below. Also, do leave a like and subscribe my channel. I'll see you in my next video. Thank you.